In this part we're gonna complete the rest of the solution of the problem. So what we have done in our last class, we found an inequality which is something like this, that P of n lies between n and 2n, and for some point it is equal to 2n and is strictly greater than n. So now we have to proceed further from this point. Before I start solving the problem, I want to say something about the polynomial P of n. If you see that the graph of n and the graph of a 2n are something like this. They both passes through the point of origin and they are linear. So if P lies between them, then it simply tells that P of n is a linear. It's a linear and it has a form ax plus b. Since it's a linear graph, it's a linear function, so it must have a form of ax plus b. And now our job is to find the value of a and b, and we are done. We are completely done. So let's see what we can do. Now if we replace this px from its linear version, then we can simply say ax plus b is smaller than or equal to 2x. And now I'm using the limit, and let's say limit x tends to infinity means x is a sufficiently large number, so ax plus b is smaller than 2x. So this equality get converted into the strictly lesser than, because we are taking x sufficiently large. And now we can divide this inequality by x, and these two x are going to be cancelled out, and this part would be 0, and we'll see this new inequality where a is smaller than 2. And since we know a is a positive number, so in this inequality we simply can get the value 1 for a. Okay, so this part is done because we know that a is a positive number and got a inequality where a is smaller than 2. So there are only one possibility, which is a is equal to 1 for an integer value. And now we have a bit evolved form of px, which is x plus b. So x plus b, now we can use our information that is given x1 is equal to 1. So it means p of x1 greater than x1, which is same p of 1 is greater than 1. So these two statements are equivalent, and now I'm going to use this. So p of 1 is r1 plus b, and which is greater than 1. So it implies that b is greater than 0. So again we got another inequality in b, that b is greater than 0, means it's a positive quantity too. If you remember, the statement of our problem is any positive integer b. So there must be a term in a sequence, let's say xl for instance, which is divisible by this b. And now we can imply that b is nothing but the p of x l minus 1, and we know the structure of polynomial, so we can write this in that form, which is xl minus 1 plus b. So this implies that b divides xl minus 1. And now that backtracking will continue like this, and we will stop at 1, or our starting value of a sequence, the first term of a sequence x1, and this implies that a number b which divides 1, and it's very clear to see that for satisfying this condition b must have to equal 1. And now, since we got a value of a and b, so we can simply construct a polynomial which is p of x is equal to x plus 1, and that is our complete proof of that polynomial.